Back in 1931, this young logician, Kurt Gödel, published a paper that completely turned the world of mathematics on its head. It was this incredible proof that showed there's a fundamental, unavoidable limit to what we can ever know for sure. And it all kicked off with one single, really big question.
So at the turn of the 20th century, this was the ultimate question. Seriously, the biggest names in math were absolutely convinced the answer was a big, loud yes. They really believed that if they could just find the right set of rules, any mathematical statement, anything at all, could be proven either true or false.
And the main guy leading this charge was the brilliant mathematician David Hilbert. He had this massive goal, what we call Hilbert's program, to build a single, perfect system for all of mathematics. A kind of master rulebook that would be the final word on what is true.
Okay, so for Hilbert's dream system to work, it had to stand on two absolutely crucial pillars. First, it had to be consistent. That just means it could never contradict itself. You can't have it prove that 2 plus 2 is 4 and also prove that 2 plus 2 is 5, right? That's a deal breaker. And second, it had to be complete. This means for any statement you could possibly think of, the system could prove it's either true or false. No gaps, no I don't knows, no maybe.
But then, this guy, Kurt Gödel, shows up. And with just one paper, he proves that Hilbert's beautiful dream of a perfect, all-knowing system was, well, impossible. And he did it with two theorems that were just devastatingly elegant.
Let's dive into the first bombshell he dropped on everybody, his first incompleteness theorem.
Okay, this is where it gets a little mind-bending, but stick with me. What Gödel proved is that for any rulebook we create, as long as it doesn't contradict itself and can handle basic math, there will always be statements out there that are true, but that we can never ever prove using the rules of that system. He basically showed us that truth is a much bigger idea than proof.
And if that wasn't enough to blow everyone's minds, Gödel wasn't done. His next move was to use the system's own limits against itself. And this brings us right to his second, equally stunning theorem. So what does this mean? It means that any system that's actually useful can't prove that it's trustworthy. Think about it. To check if a system is consistent, you have to step outside of it and use a different, more powerful system. But then, how do you prove that new system is consistent? You see the problem? It creates this endless chain of who's checking the checker.
So you're probably asking, how in the world did he pull this off? Well, the absolute genius of Gödel's proof is this clever little trick of self-reference, basically turning logic back on itself.
To get a feel for this, just think about the classic liar paradox. If the sentence, "this sentence is false," is true, well then, it has to be false. But if it's false, that means it has to be true. It's this perfect, unresolvable little loop. Gödel saw this and thought, I can build that with math.
And this is the absolute core of his argument. He managed to write a mathematical statement that, when you decoded it, was actually talking about itself. Just think about it for a second. If you could prove the statement, then it would have to be false, right? Because it claims it's unprovable. But if you can't prove it, then the statement is true. And there it is, a true but unprovable statement.
Now, how he actually did this is just sheer genius. It's a process called Gödel numbering. He basically created a secret code, a way to turn any logical statement, any proof, into its own unique number. This was the masterstroke, because it allowed mathematics to talk about itself. All of a sudden, these complex ideas about logic and proof could be turned into simple questions about the properties of numbers, something the system could totally understand.
The fallout from this was immediate, and there was no going back. The quest for absolute, total certainty in mathematics, it was over.
Yeah, the dream was officially dead. Gödel's work showed that Hilbert's grand project was fundamentally impossible. He proved that any formal system, no matter how clever or powerful, has built-in limits. But here's the really cool part. From the ashes of this dream, something new was born. By defining the limits of proof, he inadvertently laid the groundwork for the theory of computation, which would inspire pioneers like Alan Turing and lead to the birth of the computer.
But the shockwaves didn't just stop with math. Oh no. These theorems sparked a huge philosophical debate that is still raging to this very day.
This is where we get into the really fascinating minds and machines debate. See, a computer is basically a formal system. It just follows a set of rules. So, does Gödel's proof mean there are truths that a human mind can just see intuitively, truths that a machine, stuck inside its own logic, could never actually prove? It really makes you wonder about what intelligence is, and if our own consciousness is something more than just a really complex computer program. So in the end, Gödel didn't just show us a limit in mathematics. He kind of showed us a horizon for any system of logical thought. And maybe that's not a bad thing. Maybe his theorems aren't some kind of dead end for knowledge, but an invitation
an invitation to accept that the universe of what's true is always, always going to be bigger and more mysterious than the small part of it we can ever hope to prove.